The Reynolds-averaged Navier Stokes equations are time-averaged equations of motion for fluid flow. The idea behind the equations is Reynolds decomposition, whereby an instantaneous quantity is decomposed into its time-averaged and fluctuating quantities, an idea first proposed by Osborne Reynolds. The RANS equations are primarily used to describe turbulent flows. These equations can be used with approximations based on knowledge of the properties of flow turbulence to give approximate time-averaged solutions to the Navier-Stokes equations. For a stationary, incompressible Newtonian fluid, these equations can be written in Einstein notation as: the left-hand side of this equation represents the change in mean momentum of fluid element owing to the unsteadiness in the mean flow and the convection by the mean flow. This change is balanced by the mean body force, the isotropic stress owing to the mean pressure field, the viscous stresses, and apparent stress owing to the fluctuating velocity field, generally referred to as the Reynolds stress. This nonlinear Reynolds stress term requires additional modeling to close the RANS equation for solving, and has led to the creation of many different turbulence models. The time-average operator is a Reynolds operator. Derivation of RANS equations. The basic tool required for the derivation of the RANS equations from the instantaneous Navier-Stokes equations is the Reynolds decomposition. Reynolds decomposition refers to separation of the flow variable into the mean component. Because the mean operator is a Reynolds operator, it has a set of properties. One of these properties is that the mean of the fluctuating quantity being equal to zero. Thus, where is the position vector? Some authors prefer using instead of for the mean term. In this case, the fluctuating term is represented instead by. This is possible because the two terms do not appear simultaneously in the same equation. To avoid confusion, the notation will be used to represent the instantaneous, mean, and fluctuating terms, respectively. The properties of Reynolds operators are useful in the derivation of the RANS equations. Using these properties, the Navier-Stokes equations of motion, expressed in tensor notation, are, where is a vector representing external forces. Next, each instantaneous quantity can be split into time-averaged and fluctuating components, and the resulting equation time-averaged, to yield. The momentum equation can also be written as, on further manipulations this yields, where is the mean rate of strain tensor. Finally, since integration in time removes the time dependence of the resultant terms, the time derivative must be eliminated, leaving